Hi, welcome to lesson 17D, the area between two functions. We've looked at area under a curve before where the function is above the x-axis as illustrated here, that the area would just be calculated using the fundamental theorem of calculus, where we take the antiderivative of f of x, evaluate it at b, evaluate it at a, and then subtract them. So that would give us the area. And what actually that is looking at specifically is, in a way, it is actually looking at the area between two functions, where one function is the given function, and the other function is the x-axis, y equals 0. So when the graph y equals f of x is above the x-axis, the area is simply f of x minus 0, where this is perhaps the upper function, and this is the lower function. And we just subtract them, and we would find the area between the functions then. And if the curve is below the x-axis, then the upper function is the x-axis, y equals 0, and the lower function is actually the function we're looking at, where actually we get 0 minus f of x. So those results that we saw in the last class actually start to make a little bit of sense now. So when we're finding the area between two functions, we can take the difference between those two functions, and we would simplify them. So we put them in the formula, the integration formula, where y sub u and y sub l are the upper and lower functions respectively. We can put them into this integration formula and simplify them, and then we just end up having an expression that we can integrate. And same thing, we can look at it in function notation as well, being just f of x minus g of x, where f of x would be the upper function and g of x would be the lower function. So let's take a look at how all this works. So if we see two functions like this, y equals f of x is the top function, or the upper function, y equals g of x is the lower function, then as it turns out, the area between them is just the difference between them. We would integrate that and evaluate at a and b, and then we would find that area. A way of looking at this, just to simplify it a little bit, is if we were to translate both of those functions up by some vertical translation k. So if we just translate them both up by k, then those k values will actually disappear eventually when we do the subtraction. And we take the integral of f of x plus k from a to b. We take the integral of g of x plus k from a to b. We subtract them, and we end up getting exactly f of x minus g of x when evaluated from a to b. So whether one function is above the x-axis and the other is below or not, it still just works out that the area between those two functions is the integral of the difference between the upper function and the lower function. Okay, and if, for example, we had our one function, the upper function is the x-axis, y equals 0, and the lower function is y equals g of x, we would just have 0 minus g of x, and then of course that 0 just disappears, so we end up just having negative the integral of g of x dx. Okay, so just as we've seen in the past. Okay, so let's take a look at a couple examples of finding the area between two functions. So we're going to use this formula, the upper function minus the lower function, and we're going to integrate between the two boundaries, or the two endpoints of the interval. And so we're going to find the area bounded by the x-axis and the part of the function 3x squared minus 8x plus 4 that's below the x-axis. Okay, so first of all, when we have that, we need to determine where the zeros are, so we can see which part of this is below the x-axis. So first of all, we can also see just right off the bat that the lead coefficient, the sign of the lead coefficient, is positive. So that means that this quadratic, and we know it's a quadratic because we've got the square there. That quadratic is going to be opening up, and so then we can factor this. So we've got a 3x and x here. And then when we take a look at what we have to multiply to get positive 4 as the product, and then the sum of -8. Well, 3 times something plus another something times x, we need to get that -8. So suppose we try -2 and -2. So -2 times -2 is 4, and then 3 times -2 is -6, and 1 times -2 is -2. So we add those together and we get that -8 in that middle term. Okay, perfect. So therefore, the zeros are x equals 2/3 and x equals 2. Okay, so then we've got, this is 1, this is 2. I've already pre-labeled them or pre-marked them on the axes. And so 2/3 would be around here, I would say. And so then we just have to draw the curve. And halfway between 2 and 2/3 is 1 1/3 or 4/3. And so that's going to be where the vertex is. So this is just a crude sketch. So it's going to go up something like this. Whoops, something like that. And up through here. Something along that line. So we're trying to find the area bounded by the x-axis and the curve that's below the x-axis. Okay, so we're just going to then integrate this. And because we're dealing with the x-axis is y equals 0. And we're going to be using this formula. And so for the, we're going to go from 2/3 to 2. And I'm starting with the x-axis being 0, and I'm subtracting the function 3x squared minus 8x plus 4. And then I can simplify inside this before I integrate. And so then that just gives me -3x squared plus 8x minus 4 dx. Okay, then I can take the antiderivative here, and we're going to evaluate that. So we're going to have -x cubed plus 4x squared, and then minus 4x, evaluated from 2/3 to 2. Okay, so we got the 2 first. Substitute the 2 in all the way along, and then I'm going to substitute in the 2/3. And I won't be showing all the steps of this. That'll be for you to verify yourselves. And a few steps later, we would see that the result is 32/27 units squared. Okay, so please go through that and verify and make sure that you understand all the steps in order to find this area between the two curves, y equals 0, or the x-axis, and that graph, y equals 3x squared minus 8x plus 4. Okay, we now want to determine exactly the area of the region bounded by y equals 2e to the x and y equals e to the 2x and x equals 0. So x equals 0 is the y-axis. So that's one endpoint. And 2e to the x. So these are exponential functions. And remember the property about the parent function of exponential functions. All exponential functions, the parent function, if we know x equals 0, well then that would tell us that when x equals 0, that whole thing equals 1. So that means that the y-intercept is going to be 1. Okay, for a parent function. So this graph, y equals e to the 2x, that's going to have a y-intercept of 1. Now this part of the function e to the x, that will equal 1. when x equals 0. However, we're multiplying by 2. We're multiplying, that's a vertical stretch. So that function then is actually going to go through y equals 2. Okay, so the graphs are going to go, I don't know exactly how they're going to go, but let's say that this one is going to be climbing up like this, up through 2, okay, in some sort of an exponential fashion. The other curve, y equals e to the 2x, well, that goes through 1, but that 2x in the exponent, that's going to make that result, that y equals e to the 2x, that's going to climb even faster. It's going to increase faster than the first one. So it's going to go through the curve down below, or sorry, it's going to go through y equals 1, but it's going to increase faster than this other graph. So that's y equals e to the 2x. And then this function here is y equals 2 e to the x. Okay, so the one thing that we need to know now is we need to know this point of intersection. So we need to know what that is, so then we can find this area in here when we do our process. Okay, so because both the graphs cross each other, they have a point in common, so they're going to have a y value in common, and we have to find that x value. So because they have the y value in common, and they both equal y, that means they have to both equal each other. So 2e to the x equals, sorry, e to the 2x. And so what I'll do, I'm going to subtract 2e to the x from both sides. And then I'm going to factor out e to the x. So then I'm going to have e to the x minus 2 for the result here. And so either e to the x equals 0, but that's undefined. So that's not going to happen. Or e to the x minus 2 equals 0. So e to the x equals 2. I'll take the ln on both sides, or the natural logarithm of both sides. And so we've got ln e to the natural logarithm of e to the x equals the natural logarithm of 2. And so then that just tells us that x equals the natural logarithm of 2. So the x value where they intersect is actually ln 2. Okay, so that's some value, but because we're determining exactly, we'll just leave that ln 2 as ln 2, or sorry, the natural logarithm. Right? Some purists would dislike me saying ln 2 probably. We know that y equals 2e to the x is the graph that's above the other graph. So we're going from 0 to the natural logarithm of 2, and it's going to be 2e to the x minus e to the 2x dx. Okay, so we can just integrate those, find the antiderivatives of those. So the first one, well, actually, why don't you please pause the video and find the antiderivatives here, just to make sure that you're getting these correct. So pause the video now and work these out, please. Okay, so trusting that you've paused the video and worked through this, we've got 2e to the x and then minus 1/2 e to the 2x. And that's going to be evaluated from 0 to ln 2, sorry, natural logarithm of 2. And so we've got 2e to the natural logarithm of 2 minus 1/2 e to the 2 ln 2. Sorry, I keep saying that. 2e to the 0 minus 1/2 e to the 2 times 0. Okay, and in the interest of time, I'll let you calculate that. And as it turns out, when we work through the process, it ends up that that area is 1/2 unit squared. Okay, so that is that portion. I'll just tidy up that 0 here. Okay, all right, so that is example number 2. Now we're going to move on to example 3, and this one's a little bit more complicated just because there's a little bit of background work to it in order to find the zeros, because we need to determine, again, exactly the area of the region bounded by y equals x to the power 4 minus 9x cubed plus 26x squared minus 24x, and the x-axis. So first of all, I can see there that I can factor out an x from all these. Then I've got this cubic, and that cubic is not a sum or difference of cubes, and it doesn't look anything that I can factor super easily. So I'm actually going to use the factor theorem. And to get a factor, if you have a factor, then that means that any division will give you 0. There will be no remainder. So the factor theorem states if I can substitute in values to get 0, when I evaluate this, then that would be a factor. So I try 1, I substitute 1 into the bracketed portion, because I've already got that factor of x out, so I don't need to use that. So I substitute 1 in for this bracketed portion, I don't get 0. I substitute in -1, and I also don't get 0. Then I try 2, and I do get 0. So what that means, because that portion, when I substitute 2 into that, into all the x's, then that means that when I get 0, that x minus 2 is a factor of f of x. Okay? Then I'm going to use synthetic division. And because I still have a cubic, but I need to be able to factor out that x minus 2 and get a quadratic that I can factor. Now, synthetic division I find a little quicker. You can use long division, but I'm not going to go through that in this video. Synthetic division, you start out by taking all the coefficients of all of these terms in the bracket and put them all along the top. You draw this L bracket and leave a bit of space down below. And then you put this 2 that you used here in the factor theorem down outside. We bring down the 1 from the first coefficient here. We're going to multiply 2 times 1 and put the value here, the answer here, under -9. Then I add -9 and 2 and I get -7. Then I multiply 2 times -7 and place the answer here. Then I add 26 plus -14 and I get 12. Then I multiply again, 2 times 12, and put the answer here. And I can do -24 plus 24 to get 0. And that 0 is then, of course, the remainder of this division. And because I'm dividing by a factor, and of course, we'll get a suitable result, which has a 0 remainder. So the actual function f of x, which started out as x to the power 4 minus 9x cubed plus 26x squared minus 24x, has been simplified down to f of x equals x, that first x we factored out, multiplied by x minus 2, which is one of the factors we found here, multiplied by then, because I was factoring an x minus 2 out of a cubic, well, I'm dividing the cubic by x, which means that that first degree is going to be a 2 then, because I'm factoring an x out of an x cubed, I'm going to be left with an x squared. So these are then the coefficients of a quadratic. So we start at x squared, then it goes to x, and then it goes just to the constant. And then from there, I'm going to factor this, and this x squared minus 7x plus 12 gives me x minus 3, x minus 4. So then all the zeros for this are going to be 0, 2, 3, and 4, okay, from these factors here. Okay, and we know the lead coefficient of the function is positive. That means that the graph opens up. So we see this here is +1. The graph's going to open up. And so then it's going to give us a bit of a W form. So we're going to have 2, 3, 4, and there's 1. So the graph's going to look something like this. It's just again, a very crude estimation of the curve. It's going to go something along this line. Okay, and then when you set this up, it's going to look like, from the first portion is underneath the x-axis, so it's going to be 0 minus this function between 0 and 2. So the 0 is going to be subtracting this. So that's why we have the negative here. Plus, from 2 to 3, it's going to be f of x minus 0. And then again, minus is going to be underneath. So it's going to be 4, from 3 to 4, this negative f of x dx. And we're going to go through all this. And I'm just going to use the GDC. I'm going to show you the GDC version of this, where we use the absolute values and evaluate from 0 to 4. And then that will give us the area under the curve. So if you wanted to do it by hand, it would be a lot of grunt work to get through all this stuff. But what we can do, which is a little bit easier, if we go to Math 9, and we'll just go from 0 to 4, all the way up to 4. And then in here, we're going to do the absolute value. And the absolute value, if I'm not mistaken, is, I'll go second 0 and go to abs right there. That's absolute value. And then I'll put in the function. And the function was x to the power 4 minus 9x cubed and plus 26. Keep having to come down from the exponent. Plus 26x squared minus 24x. And then I just get outside here, put an x. And then from there, I just press enter. And Bob's your uncle. Now, this is not the exact answer, and I apologize for that. I guess I could change that, can't I? Let's change that. Let's go to alpha window. Go down to 4. And we change that. So now all of a sudden we know that that is 29/30ths. So that's 293/30ths units squared. Okay, but that of course is approximately equal to 9.76, 9.76666, etc., which is to 3 significant figures, 9.77 units squared. Okay, and so that's how all that works, but we're taking the upper function, subtracting the lower function, we're doing the antiderivative after we simplify that expression, and then we evaluate at the endpoints. Okay, so that is it for today. So thanks for watching, and we'll see you in class.